Hello, welcome back to Earth Materials. Today I'm going to be talking about chemical sediments. So these are materials that are precipitated out of solution. First I'm going to talk about salts, how they're formed and how they precipitate. Then I'm going to talk about some common chemical sediments, and then I'm going to finish up with some carbonate classification. So this lecture should provide a foundation for students to understand how salts form, especially gypsum, halite, and sylvite, identify some common chemical sedimentary rocks and minerals, especially calcite, aragonite, and apatite, and then to apply the Dunham carbonate classification diagram. Okay, first, how do chemical sediments form? Well, one of the simplest ways is simply to evaporate seawater. Now, seawater contains several dissolved solids in it: calcium sulfate, sodium chloride, and potassium chloride. And seawater is undersaturated with respect to the three main minerals that take up these elements: gypsum, halite, and sylvite. The degree of undersaturation is greatest for gypsum, then for halite, and then for sylvite. But the concentrations are quite different. It turns out that calcium sulfate is in very low concentration in seawater. Halite, sodium chloride, there's a lot of halite dissolved in seawater, and there's a little bit of sylvite that's dissolved in seawater. So quick check, if you evaporate a pan of seawater, what is the least abundant salt that is likely to form? And the answer is gypsum. Gypsum has the lowest concentration, at least on a molar basis. Now, as I mentioned before, these minerals are undersaturated, but to different degrees. So if we look at the solubility product of calcium and sulfate in solution, and we look at the activity product of calcium and sulfate, we find that gypsum is about 2.5 times undersaturated. If we do the same for halite, we find it's about 600 times undersaturated, and if we look at sylvite, it's about 40,000 times undersaturated. So in terms of undersaturation, gypsum is a little bit undersaturated, halite moderately, sylvite highly undersaturated. So what does that mean? If you evaporate a pan of seawater, what is the first salt that would precipitate? And the answer is gypsum. As we evaporate seawater, the concentrations of the ions increase, and so gypsum is the first to reach saturation. Now, if we take some volume of seawater, let's imagine we have a kilometer of seawater, and we evaporate it down to about 1/3 of its original volume, gypsum will saturate. And if we evaporated all of the seawater, we'd end up with about 3/4 of a meter of gypsum. Now, if we evaporate 90% of the seawater, at that point, halite begins to saturate. And if we evaporate a kilometer of seawater, we'd end up with almost 14 meters of halite. Whereas with sylvite, we have to evaporate a lot more seawater to hit saturation, about 95% of it. And if we evaporate a kilometer of seawater, it would have about 7/10 of a meter of sylvite. Here's an example of the Sicily Basin from the late Miocene, and this gives you a sense of how these salts can occur. So here, for example, is a lower gypsum zone, here's a halite zone, and here is a sylvite zone. And you can see it goes back and forth: sylvite, halite, sylvite. There's an upper gypsum zone, lower gypsum zone. But these are thought to reflect the evaporation of seawater until it hits these saturation states. I thought I would talk a little bit about the structure of some of these minerals. Halite and sylvite have the same structure. The cation is in octahedral coordination with chlorine, and these make a cubic structure. Here's halite, here's sylvite. Here is a crystal of halite, and in fact these are crystals of sylvite. And you can see they have this cubic symmetry to them. Gypsum is quite different. Calcium is in a 6-fold coordination, but it's not octahedral. It's this sort of funny-shaped polyhedron. And what holds it together are water molecules, which occupy interlayer sites, and these become very, very weak. That's why gypsum is so soft. Here's an example of gypsum from Lechuguilla Cave in New Mexico. Now, one of the curious things about salt deposits is that they don't really follow the concentrations of the different minerals in solution. So, for example, we see thick beds of gypsum, moderately thick beds of halite, thick beds of gypsum. That's not what you would predict if you were simply to evaporate seawater completely. And we see here that there can be beds of gypsum that reach tens of meters in thickness. Well, if a kilometer of seawater evaporated gives you only 3/4 of a meter of gypsum, how do you get 10 meters of gypsum, right? You don't have 15 kilometers of seawater to evaporate in these shallow basins. So the most common interpretation of the formation of these gypsum beds is that there is a reflux mechanism where there's a shallow basin that has a restricted opening. It reaches saturation with respect to gypsum. The gypsum settles out. There's more seawater that comes in. It also reaches gypsum saturation. More gypsum settles out. But it doesn't evaporate to the point where halite or sylvite are precipitated. It is true that if the basin becomes more restricted, then that seawater can hit halite and sylvite saturation, and then we can begin to deposit large thicknesses of halite, here tens to even hundreds of meters. This is thought to have happened in the Mediterranean during the Messinian salinity crisis, where the Mediterranean Sea pretty much dried up and created these thick deposits of halite and sylvite. Okay, so at this point, I hope you have a sense of how salts form through the evaporation of seawater to produce gypsum, halite, and sylvite. Let's talk about some common chemical sediments. Carbonates are some of the most common chemical sediments. They consist dominantly of calcite, dolomite, and to some degree, aragonite. Here is the calcite structure. Calcium is in octahedral coordination. These little trigonal planes are the carbonate molecule. And you can see the little planes are flying in this direction in this layer, this direction in this layer, and so on, back and forth and back and forth. And the same is true for the calcium octahedra. They're pointing out towards us in this layer, pointing away from us in this layer, towards us in this layer, away from us in this layer. And again, this is what gives rise to the high symmetry of calcite. It belongs to the hexagonal crystal system, and that's because the alternation of the pointing directions of the carbonate and the pointing directions of the calcium octahedra even out the axes so that they are perpendicular. Okay, this is the structure for calcite. This is the structure of dolomite, and it's very similar. The only difference is that every other layer contains magnesium rather than calcium. So we have a calcium layer, magnesium layer, magnesium layer, and so on. Calcite, dolomite, and magnesite are all related to each other by calcium-magnesium exchange, which is not very ideal thermodynamically. And as a consequence, these three minerals have solvi between them. So here is the calcite-dolomite solvus, and here is the dolomite-magnesite solvus. Now, the data here don't even go up high enough in temperature to close out the solvus, but if you could go to high enough temperature without melting or decarbonating the carbonates, then this would close off at very, very high temperature. So what does this mean? This means that the magnesium content of calcite coexisting with dolomite can give us a temperature. To some degree, that's what people use in chemical sediments to determine temperatures. So here, for example, is the mole percent of magnesium carbonate in calcite, and this is versus water temperature. So these are various organisms, barnacles and echinoids and forams and calcareous algae. They all have different temperature dependencies, which is actually reflecting a biotic effect. Nonetheless, these kinds of relationships can be used to determine temperature. So here, for example, is the magnesium-calcium ratio in millimoles per mole versus sea surface temperature for several different species of foraminifera. So this is Globeriginoides ruber, white variety, Globeriginoides ruber, pink variety, and so on and so on. These are some of the data, and you can see that not every species has exactly the same temperature dependence. So these three genera fall towards the bottom of this regression line, and these genera fall above the regression line. And that just tells you that different species have different temperature dependencies, so they all have to be calibrated independently. Now that's calcite. Many organisms precipitate aragonite. Here is crystalline aragonite, but these sorts of large seashells commonly contain the mineral aragonite rather than calcite. Aragonite has those same trigonal carbonate molecules in them, but it has calcium that's in ninefold coordination. So this is a very compact structure. It's actually much denser than calcite. And so if we look on a metamorphic pressure versus temperature diagram, we find that aragonite is stable only at very high pressure, many, many kilometers below the surface of the Earth at room temperature. So what's going on here? How can these organisms be precipitating aragonite? Well, it's a simple fact that minerals don't always precipitate at equilibrium. The equilibrium mineral at room temperature and pressure is calcite, but these organisms are precipitating aragonite. And what that means is that these shells will not want to be stable after being buried. They'll want to invert to calcite. So if it's unstable at Earth's surface, what process would then be responsible for transforming that aragonite to calcite? What would we call that? And the answer here is diagenesis. It is absolutely true that metamorphism will transform aragonite to calcite as long as the PT conditions are in the calcite stability field. But here we're talking specifically about sedimentary rocks, and diagenesis is a sedimentary rock forming process. Let's look at a couple of other chemical sediments. Chert is made of opaline or cryptocrystalline silica. Commonly, it's a deep sea sediment that represents recrystallized diatoms or other microsilica particles. Here are some scanning electron microscope images of diatoms. These can be only a few microns across. When it accumulates, it forms chert. This chert, of course, was used by Native Americans to make projectile points. Now, chert is the general name for these siliceous sediments, but it can have different trade names depending on what color it is. Flint is gray or black. That has a lot of organic matter in it. Jasper is a red variety of chert that has hematite microcrystals in it. Novaculite is white. Commonly, it's been a little metamorphosed, and it's nearly pure silica. And chalcedony is a fibrous variety. So here, for example, is jasper, and down here, these would be flint. Another chemical sediment I want to talk about is phosphorite. Phosphorite occurs when there are upwelling zones. So here off the coast of California is an area where there's cold water that's upwelling. There's a lot of productivity. So there's a lot of apatite that's precipitating and accumulating in these phosphorite deposits. That's what these red dots are. So here's the mineral apatite, and here is francolite. Francolite is a fluorine and carbonate-rich apatite. And then last, I want to talk about banded iron formations. Banded iron formations represent interbeds of jasper, so red chert, and either hematite or magnetite or both, as well as anchorite and hydrous iron silicates. These can occur in these rocks as well. Banded iron formations, or BIFs, are an important ore of iron. In fact, that's where most of our iron ore has come from historically. But they're restricted to the Precambrian, and about 90% of them occur within this age range, 2 to 2.5 billion years ago. Well, this time corresponds to the Great Oxidation event. This is when photosynthesis evolved on Earth. So a lot of the ferrous iron that was in solution in low oxygen-bearing waters was upwelled, and microorganisms, making a lot of oxygen, caused the oxidation of iron to precipitate iron oxides and silicates, as well as this chert that has so much iron oxide in it. Okay, so at this point I've covered the main chemical sedimentary rocks and their minerals. So let's finish up with the Dunham classification of carbonate rocks. The Dunham classification mainly focuses on the degree to which mud is present in a carbonate rock, and then what the coarse particles are and how they're held together. This diagram of the Dunham classification comes from a website at University of Texas Bureau of Economic Geology, and mostly I'm going to focus on this top section up here. These are the more common limestones that we see. And it comes down to the amount of mud. If there is less than 10% grains, so here's a grain and there's a grain and there's another grain, here's another one, but otherwise almost all this material in here is mud. If it's less than 10% grains, then we call it a mudstone. If it's more than 10% grains, but the grains don't touch each other, then it's called a wacky stone. If the grains touch each other, so they are bearing the load, they support each other, but there is still mud present, then we call it a pack stone. And then if the grains are touching each other and supporting each other, but there's no mud in here, then it's called a grain stone. Why is this blue? Carbonate petrologists, when they have thin sections made, will have the epoxy stained blue so it shows up more clearly in photomicrographs like this one. So wherever you see blue, that means it was empty space. There are other types of carbonates in the Dunham classification. A bound stone, this is an example of a bound stone, means that the different sedimentary components were bound together while they were being deposited. So filamentous algae can bind grains together. A float stone has very large grains which are floating in a mud matrix. So this is a type of wacky stone. A rud stone or rood stone has very large grains that touch each other. So this would be a pack stone. But the difference is that these grains are very, very large, tens of millimeters across. And these are characteristic of rudist clams, which form a reef structure. This is what gives rise to the name roodstone. What baffle stone means is that there are structures that stick up into the water column such that they act as baffles to wave motion. As a consequence, fine-grained material can fall down in between these upright baffles. And then a bindstone is, again, where there are binding organisms that hold all of the constituent grains together. Okay, I know I went through that very quickly. My hope is that if you had thin sections or rock samples, that you could compare them with the images from the Dunham carbonate classification diagram to classify carbonates. All right, thanks. Okay, now just a fun question. Your choice. Which do you think is funniest? I'll let you decide what your answer ought to be.